In Cycle 2, Lesson 3, we're going to be working with quadratics again. We're going to be solving some problems. We're just going to sort of continue. Some of this will be a review of grade 10 still, and some of it will again be extension, as we've done in some of our previous lessons involving quadratics in this course. So there's going to be a few different things. Let's start with quadratic in standard form. What happens if we want to solve it? Solving it means to find the zeros, to find the x-intercepts. We know that when we have a quadratic in standard form, probably the easiest way is to factor it. And so if we can think of two numbers that multiply to give the last term and add to give the middle term, then we can factor it, which I will do. 2 and 1 would multiply to give 2 and add to give 3. And if they're both positive, that works out. Now remember that when we want to get the zeros of a quadratic, if it's in factored form, if it's just a basic quadratic like this, then we need to we can pull out the number and change the sign. So we'd have -2 and we'd have x equals -1. We're not really pulling out this number. I mean, it is. These are the zeros, s and t, as we've called them in previous formulas of this quadratic. But it's if I stick -2 in for x, then -2 plus 2 is going to give me 0, which will make the equation balanced. Or if I stick -1 in, then -1 plus 1 is going to give me 0, which will make the equation balanced. So that's one way of factoring or of solving a quadratic. We do it by factoring. Another way we do it, if we can't factor it, we could use the quadratic formula. So the quadratic formula is going back to ax plus by plus c, and we're just filling in the different values of what a, b, and c are into the quadratic. So a would be, I'm just going down here where we got a, b, and c going into the formula and seeing where we put the different values in, right? So for a particular quadratic like this one, a is 1, b is 3, c is 2. And so when I fill these into the actual quadratic formula, I'd have negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And again, I can highlight the different parts for us. A, b, and c, respectively. So when I take off the brackets and start simplifying, I have -3 plus or minus the square root of, well, 3 squared is 9 times, or minus 4 times 2 is 8. So it's going to be 9 minus 8, which will be 1. And 2 times 1 is just 2. So -3 plus or minus the square root of 1 over 2, which is -3 plus or minus 1 over 2. So I'm going to have two different things. This plus or minus gives me, if I do a plus, I'd have -3 plus 1 over 2, which would give me -2 over 2 or -1. That would be one of my solutions. Or if I was to do the minus sign, I would have -3 minus 1 over 2, which would be -4 over 2 or -2. And those match up with the answers I got above because it's the same equation. I need to get the same answers, obviously. I wouldn't use the quadratic formula unless I couldn't factor something. And obviously this is a fairly easy, I hope anyway, a fairly easy quadratic to factor because it's pretty easy to find out two numbers that multiply to give 2 and add to give 3. But if you can't factor something, then you can go to the quadratic formula. Now here's a problem involving quadratics. A factory is to be built on a lot that measures 80 by 60 meters. A lawn of uniform width equal to the area of the factory must surround it. How wide is the strip of lawn and what are the dimensions of the factory? Start with a label diagram. We're definitely going to need a diagram to help us visualize this one. So here this can represent our our lot. So it's 80 by 60. There's going to be a factory built in the middle of it, and it's going to have a uniform strip of lawn around it. So I'm going to try to make this look fairly uniform. So the lawn is going to be all out here. I didn't color the whole thing, and it's going to be out in that area there. So the factory is going to be in the middle. So if the lawn is uniform, that means that I don't know what the width is. That's one of the things we're being asked to solve. How wide is it? But why don't I let x represent that? So if x is the width, I'd have an x width here, but I'd also have an x width here, right? And I'd have a width of x here and here. The reason why I'm pointing that out is because that lets me know how long the length of the factory is going to be. It would be the 80 meters minus the two x's, one on either end, would give me the length of this long side of the factory. So it would be 80 minus 2x. Likewise, the short side of the factory would be 60 minus 2x, because we take the 60 here and subtract these two x's here to get 60 minus 2x. So there's the length and width of the factory. We also know that the area of the lawn has to be equal to the length of the factory, equal to the width of, equal to the area of the factory. So the factory needs to take up exactly half the space of the lot. So we know the area of the lot. That's easy to calculate. Area of the lot is 80 times 60 meters, which is 4,800 meters squared. That's for the lot. The area of the factory is going to be half that, right? 4,800 divided by 2. So it's 2,400 meters squared. So we know that x is the width of the strip of lawn, but we don't know what it is. That's what we're supposed to find out. Well, now we've got enough information that we can make up an equation and solve it. So I can just use these dimensions here, since they involve everything we need. We know the length, we know the width, we know the area of 2,400 of that inside box. We can create an equation and solve that for x. So I know that length times width, length times width equals area, right? Go back, let's write it that way. Length times width equals area, but the length of the inside box is 80 minus 2x. The width of the inside box is 60 minus 2x, and the area of that box is 2,400 meters squared. I can solve this equation for x. Now there's a couple ways of doing it, but maybe what I'll do in this case is let Desmos help me again. I can put it into standard form, or I can put it in any form. I could type it into Desmos like this, to be honest. Well, not quite like this. I would have to bring the 2,400 over to the other side. But let's put it into standard form. That's good practice anyway. So I'm going to do FOIL to expand this out. So first times first, 80 times 60 gives me 4,800. And then outside times outside, 80 times 2x gives me negative 160x. And then negative 2x times 60 gives me negative 120x. And then last times last, negative 2x squared times negative 2x squared gives me positive 4x squared. And I can bring that 2,400 over to the other side. I get negative 2,400. So that equals 0. Now, if I collect my like terms and put it in proper order where the x squareds come first, I'll have the 4x squared first. Then I collect my like terms. I've got a negative 280x. And I collect my constant terms. 4,800 minus 2,400 is 2,400. So now I've put this into a nice standard form equation. I could graph it the way it is, but I could also factor it, right? Whenever we're trying to solve an equation, especially a quadratic one, it's a good idea to common factor first. So we should look to see if we can take out any common factor. And if you take a look at the three terms, it should be obvious pretty quickly that we can take a 4 evenly out of every term. 280 divided by 4 is 70, and 2400 divided by 4 is 600. So taking out that common factor just gives me an easier thing to try and solve. So I can try and factor this, and that's certainly possible. Or I could use decimals, or maybe I won't. Maybe I'll actually just do it all algebraically, since we have moved on to algebraic things in this unit. But assuming that this looks like a difficult one to factor, maybe you can factor it, and I'm sure you could, if you spend some time at it, but let's say we couldn't factor it. That would be where the quadratic formula would come into play. So it's negative b, so negative, and b is negative 70, so negative 70, plus or minus the square root of b squared, minus 4 times a, and I'm just doing the part inside the brackets after I've taken out the common factor. So a is 1, and c is 600, and it's all over 2 times 1. So negative 70 is just positive 70, and 70 squared is 4,900, and minus 2,400, all over 2. 4,900 minus 2,400 is 2,500. When I take the square root of that, that actually works out to be 50. So that whole square root thing ends up being 50. So again, I'm going to get two answers. 70 plus 50 divided by 2 equals 60. And 70 minus 50 divided by 2. 70 minus 50 is 20 divided by 2. That gives me 10. So being a quadratic, I've got these two solutions, x equals 60 and x equals 10. Well, that can't make sense, can it? Well, it can make sense as far as the algebra goes, but it can't make sense in terms of the answer to our problem, because I can't have two different widths of the lawn and have them both work out. A quick glance at this particular problem shows me that I can rule out the 60. Why? Well, let's go back and look at this. The width is 60 minus 2x. So if x equals 60, I'd have 60 minus 2 times 60. I'd have a width of negative 60 meters. That's impossible, isn't it? Likewise, the length is 80 minus 2 times x, 2 times 60. I'd have 80 minus 120. I'd have negative 40 meters. In neither case does that length make sense. So that's why I can rule out the 60 in this case. Yes, it's the solution to the quadratic, but it's a nonsensical solution to this problem. So the width that makes sense is 10 for the width of x. So x is 10. What are the dimensions of, how wide is the strip of lawn? Okay, so sorry, I've taken a lot of space here, but the strip, not step, the strip is 10 meters wide, and I'm also supposed to say the dimensions of the factory. So remember, the factory was 80 minus 2x. So the length of the factory would be 80 minus 2x. So 80 minus 2 times 10. So it's 60 meters. And the width would be 60 minus 2x. So 60 minus 2 times 10 would be 40 meters. And there's the solution to our problem there. So using some ingenuity, using what we know about quadratics, and playing around with the numbers a bit, then we were able to solve this algebraically. Problem 2. Again, just some more general sort of quadratic review type things that we should know. A water balloon is catapulted into the air from the top of a building. The height t, or height h at t, in meters of the balloon after t seconds is given by this equation here, h at t equals negative 5t squared plus 30t plus 10. What's the initial height of the building? Well, maybe a little sketch before I even do this will come in handy. Sketches are always a good idea. So, let's see. Let me get rid of that. So let's say we've got just a freehand sketch here. Here's a building. Someone launches a balloon up in the air and it comes down, right? So it's going to go up and it's going to come down. If I was to do time versus height, then the graph would look something like this. It would start at some height about here. It would go, again, this is time versus height now. It would go up for a while, then it would come down, and eventually it would hit the ground and go splat, right? So this is my h-axis, height. This is my time axis here. So what was the initial height of the building? Well, the height of the building is going to be wherever it was launched from. It's going to be my h-intercept. You may recall that when quadratics are in standard form, the c value is my y-intercept, or in this case, my h-intercept. So I can tell just from looking at the equation that the height of the building was 10 meters from the c value. Another way of explaining that is saying that when this starts, t is 0, we're starting at the height from the top of the building at 0 seconds. If you put 0 into that equation, found h at 0, you'd find that h at 0 equals 10. So same idea. When will a balloon hit the ground? Well, that's down here, right? That's one of our zeros. So we need to find out what the 0 is for that. So we either need to factor or we need to use the quadratic formula. Factoring is always easier if possible. So let's start with the equation. I'll put 0 in for height because that is the height of the ground. And I will try to see if I can factor this one. We always look for a common factor, and it turns out that -5 can be taken out as a common factor in this case. So that's helpful. When I do that, what I've got left in the brackets is t squared minus 6t minus 2. Sadly, I can't think of anything that multiplies to give -2 and adds to give -6. And I say sadly because that means I have to resort to using the quadratic formula. But again, I'm only going to use it, I'm going to choose my AC and A, B, and C values from what I've already factored here inside the brackets, just to keep my numbers a bit smaller. So using the quadratic formula, I've got -6 plus or minus the square root of -6 squared minus 4 times A, which is 1, times C, which is -2, all over 2 times 1. So that becomes +6 plus or minus the square root of 36 plus 8, all over 2. So 6 plus or minus the square root of 44. Square root of 44, or 44 is not a perfect square. That's why I wasn't able to factor it, because I'm going to get a decimal answer. But putting that in my calculator, again, I have to do them one at a time, right? So I'll do 6 plus the square root of 44. Not square roots. 6 plus the square root of 44. And then I will divide that answer by 2. Notice how I put brackets around it to keep the order of operations good. 6.16, let's say. So one of the answers is x equals, or I guess it's not x, is it? It's t. So I mostly use t as my variable because that is my equivalent of x in this case, 6.12. The other one, if I stick a negative, use this negative instead of the positive, I can just change that in here to a minus, and I got -0.16. Again, we have to think about what makes sense. In this case, negative time doesn't make sense. That would just be if I extended the parabola backwards. This is where it would get the hit at -0.16, but I want the positive one, which was 6.12. So it took 6.12 seconds to hit. So the actual answer in this case is 6.12 seconds. When will the balloon reach a height of 30 meters? Okay, in that case, for C part, really 30 meters is a y value, right? So, or the equivalent of a y value in this question. It's basically saying h at t equals 30. So I'm sticking 30 in for y, and then I'm going to solve it again for t. So if I bring the 30 over, I need to put it in standard form. If I bring the 30 over, I got negative 5t squared plus 30t. And I have 10 minus 30 gives me negative 20. So again, I can try to see if I can factor it. I could take a common factor of negative 5 out again. I've got t squared minus 6t plus 4. But unfortunately, yet again, that's not factorable. So I have to resort to the quadratic formula. So negative 6 plus or minus square root negative 6 squared minus 4 times a times c divided by 2 times a. If you do the quadratic formula a few times, you start to get pretty fast at it. So there's my numbers. I get 6 plus or minus the square root of 20 over 2. And again, that's something I'm going to have to just go to my calculator for. But I've already got actually most of it there. So I got 0.76, 0.76. And let's see what the other one I get is. That would be if I have a 6 minus the square root of 20 over 2. So again, oh, no, I already did the minus, so I'll change it back to a plus. So if I do the plus one, I'd get 5.24. So again, that's doing one with the plus and one with the minus. Both of these are positive numbers. That actually makes sense. Where's my sketch? I assume that 30 meters is probably somewhere up around here, which means it's going to hit it once at about, what did I say, 0.76, and another time coming back down at 5.24. So there's actually two logical solutions for when it's at 30 meters. I'm not going to discount it like I crossed off the negative time for part B. There's actually two answers for part C. What are the domain and range for this function? Well, the domain is going to be all real numbers. We know quadratics are always all real numbers, but there is a restriction for this one. And it's not x, it's t again. So t is a member of the set of real numbers. It's got to start at time 0, and it's going to keep going till it hits the ground, which we saw was at 6.12 seconds. And so t is going to be between those two values. As far as the range goes, I need to know what the vertex value is. It's going to be below the vertex, so the range is going to be a height is all real numbers. And it's going to stop at the ground, so it's not going to go below 0, but I don't know what that upper limit for the vertex, the y value of the vertex is. So I've got a couple of options. I could either put it into into vertex form by completing the square, or I could take the two zeros, get the axis of symmetry, and plug that into my equation. Or I could even take these 2 points and get the axis of symmetry from them, because I can get the axis of symmetry from any 2 points. Maybe I'll go that route. And again, I know this question is actually taking quite a bit of space. So you might need some extra paper beyond the handout in order to write this all out, but maybe I'm just writing large. So in order to get the last part that's going to go in here for my my y value, my vertex, I'm going to take, maybe I'll just go sideways here. I'm just going to take this and get the axis of symmetry, which will be, axis is going to be y equals, add these together, it's the average of these two values, divide by 2. I'll just do that on my other calculator right now because it's just a little bit easier. And I got 3, so that's easy. So, it's not y, is it? It's x or t in this case. So it's a vertical axis, so it's t equals 3. So in other words, at 3 seconds, that's where the vertex is going to occur. But I need to find out what h at 3 is now to find out what the y value is at that point. So it would be negative 5 times 3 squared plus 30 times 3 plus 10. So that would be negative 45 plus 90 plus 10, which would be 55. So the vertex, going back to my sketch here, occurs at 355. So it's going to be, that's the highest the range can reach up to, 55 meters, and that would be h. So h is between 0, the ground, up to the vertex of 55 meters. Okay, back to talking about zeros for a minute. Quadratic functions can have 2, 1, or no zeros, which we also sometimes call x-intercepts or roots or solutions. So graphically, that could look like this. There's 2 zeros. There's an example opening up, and it crosses the x-axis in 2 places. Here's 1 0. There's, again, it's opening up. They could open up or down, but I've just drawn pictures showing up. So when there's only 1 0, it's when the vertex is sitting right there on the x-axis. And when the vertex is opening, when it's opening up and it's above the x-axis, if it's not touching it at all, then there's no zeros, right? So that's what it looks like graphically. Again, it could be opening down, but same idea of 2, 1, or 0 zeros. Depending on the form of the equation, here's how you can tell how many zeros there's going to be. Factored form's the easiest. If it's in factored form, and it's got 2 different zeros that you can see, 2 different factors, like this, there have to be 2 zeros. The zeros are 5 and 4. If it's in factored form and you've got 2 of the same factors, as in a perfect square, there's only 1 0. And if you can't put it in factored form, then there's no zeros. If it's in vertex form, what we want to look at is A and K. A tells me the direction of opening, and K tells me where the y value of the vertex is. So if A and K are different signs, so in other words, if K is negative, for example, like it would be here, K in this case would be -1, right? So if K is negative, but the parabola opens up with a positive A value, it's going to cross the x-axis in 2 places. Or vice versa, if K is positive and A is negative, it'll still cross in 2 places. So we're going to have 2 zeros if A and K have different signs. If there's no K in the equation, like in this one, there's no plus or minus anything on the end of this, we assume it's a 0. That means it's sitting right on the x-axis. And if the vertex is sitting right on the x-axis, then there's going to be 1 0. So think of that if there's no K value. Different signs there for A and K. If A and K have the same sign, that means the vertex is either above the x-axis and it opens upwards, or the vertex is below the x-axis and it opens downwards. Either way, there's no zeros. Finally, we have standard form. And in standard form, we want to use something called the discriminant. That's the part that you can find under the square root in the quadratic formula. So b squared minus 4ac, right? If we can take the square root of b squared minus 4ac, then when we add it and subtract it, again, we're going to get two different solutions, and we're going to get 2 zeros. So if b squared minus 4ac, it turns out to be a positive number, there's 2 zeros, as you can see in this case. If b squared minus 4ac turns out to be exactly equal to 0, then we're only going to get one solution, because whether we add or subtract it, it's going to still give me the exact same answer in both cases. And if b squared minus 4ac ends up being a negative number, remember, this is what we take the square root of. We can't take the square root of a negative number, and there's going to be no zeros. the question stops there, right? So without solving, we want to find the number of roots for each one of these questions. So in A part, it's in factored form, and we've got two different factors. And they have, so since they're different factors, there's going to be two zeros. In B part, it's in vertex form, so I'm looking at A and K. K is positive. A is also positive, which means that the vertex is above the x-axis, but it's opening upwards, so it's never going to cross the x-axis, so there's no zeros. And in this last one, because it's in standard form, we have to do the discriminant, so b squared minus 4ac, and see if it's positive, negative, or equal to 0. So b is 1 minus 4 times a times c gives me 1 plus 8 times 15 would be 120, I guess. So it doesn't matter what the value is, it's positive. I can take the square root of it. I'll get two different zeros when I do it. Last example, for what values of k does f of x equal kx squared plus 16x plus k have two different zeros? Start with the discriminant and solve. Not solving, solve. So what we can do is we can plug in this into the discriminant. So b squared minus 4ac. In this case, we've got an a value of k, we've got a b value of 16, and we've got a c value of k. So let's see what we've got. So b squared minus 4 times a, which is k, times c, which is also k, gives me 16 squared is 256 minus 4k squared. And I'm going to set this equal to 0, but what I want is I want k to give me a value that's actually greater than 0. So maybe what I'll do is I'll just go to Desmos in this case to graph this, and I'll do y equals negative 4x squared plus 256. 4x squared plus 256. So I want values that are going to be above 0. So anything between negative 8 and positive 8 are going to work. That's going to give me, as you can see, y values that are above 0. So from this, I can tell that if k is is between negative 8 and positive 8, wasn't it? So negative 8, if k is between negative 8 and positive 8, then I will have numbers that come out above 0 in that case, and my discriminant needs to be above 0 in order to have two zeros. So this would be my solution for this last one. So that's a little bit of an extension problem. So again, a bit of a smorgasbord of different things that we can do with quadratics, and again, just keeping our quadratic math skills tuned up. Good luck with the practice, and let me know if you have any questions.